Hello, welcome to another exciting class in physics. I am Wuzo Gift. Our topic today is simple harmonic motion, part 4. Let's go on to see our objective for this lesson. By the end of this lesson, you should be able to calculate the energy of a simple harmonic motion. And you should also be able to explain force vibration and resonance. In our previous lesson, we were able to show the relationship between linear acceleration and angular acceleration of a simple harmonic motion. But in today's lesson, our focus will be on the energy of a simple harmonic motion. In a simple harmonic motion, there is always a restoring force which tries to pull a vibrating body back to its position of equilibrium. Since force and displacement are involved, work is done and energy is expended. Don't forget, energy is the ability to do work. Going on, let's talk about the energy of a simple harmonic motion. Whether an object is at rest or in motion, it possesses energy. The energy of a simple harmonic motion is simply the energy possessed by a body undergoing simple harmonic motion. In order for us to study this energy, we shall be considering two examples of simple harmonic motion, which are the motion of a simple pendulum and the motion of a mass attached to an elastic spring. Going on, it's important for you to know that the total energy of a simple harmonic motion is the sum of its potential energy and kinetic energy. And recall that potential energy is the energy possessed by a body at rest. There are different types of potential energy, which include gravitational potential energy, magnetic potential energy, electric potential energy, and elastic potential energy. Next, kinetic energy. Kinetic energy is the energy possessed by a body in motion. Mathematically, kinetic energy Ke is equal to half mv squared. This shows that kinetic energy depends on the velocity v. Just like I said earlier, in a simple harmonic motion, total energy is equal to kinetic energy plus the potential energy at any point in time. Recall from the part 2 of this topic that velocity at maximum displacement is 0. And since the kinetic energy depends on the velocity, the kinetic energy at maximum displacement is also 0. Therefore, the total energy at maximum displacement is the potential energy, and we call that energy maximum potential energy. The maximum potential energy is reached when the potential energy is the only energy in the system. Also recall that at equilibrium position, velocity is maximum. Therefore, the kinetic energy is maximum and the potential energy is 0 because the displacement is 0 at equilibrium position. Therefore, the total energy at the equilibrium position is equal to the kinetic energy. And we call this kinetic energy maximum kinetic energy since it is the only energy available at such point. Now, from the law of conservation of energy, which states that the total energy at any point in the system remains the same, we have that the total energy is equal to PE plus KE, which is potential energy plus kinetic energy, and is also equal to the potential energy maximum and equal to the kinetic energy maximum. Now, having seen that, let's go on to consider the motion of a simple pendulum. Recall that a simple pendulum comprises of a mass hanging on one end of a string that is fixed on the other end to a rigid body. When this bulb is displaced as an initial angle and released, it continuously vibrates to and fro about its equilibrium position, as seen in this diagram. Since the force of gravity acts on the hanging bulb, the potential energy of a simple pendulum is the gravitational potential energy. And gravitational potential energy is given by the formula PE equal to mgh, where m is the mass, g is the acceleration due to gravity, and h is the height. At the extreme position, potential energy is maximum. Therefore, PE is equal to mghm, where hm represents maximum height. Also, as we have seen earlier, at the equilibrium position, kinetic energy is maximum, which implies kinetic energy Ke is equal to half m v subscript m squared, where v subscript m represents the maximum velocity. Now the total energy, which is given by PE plus KE equal to maximum potential energy equal to maximum kinetic energy, can also be written as total energy equal to mgh for potential energy and half mv squared for kinetic energy, mgh subscript n for maximum potential energy, and half mv subscript m squared for maximum kinetic energy. When we equate these two expressions, we have half mv subscript m squared is equal to mgh subscript n, and if we divide both sides by m, we will have Vm squared is equal to 2gh subscript m. And when we take the square root of both sides, we will be left with Vm is equal to square root of 2gh subscript m. Therefore, the maximum velocity of a simple pendulum is V subscript m is equal to square root of 2gh subscript m. Having shown the formula for calculating the energy of the motion of a simple pendulum, let's go on to find an expression for calculating the motion of a mass attached to an elastic spring. For the motion of a mass attached to an elastic spring, the potential energy is elastic potential energy. And the formula for calculating elastic potential energy is PE equal to half Ks squared, where K is the force constant and S is the displacement from equilibrium position. At maximum displacement, potential energy is maximum, that is, PE is equal to half Ka squared. Recall that at maximum displacement, S is equal to A, where A is the amplitude of the motion. The kinetic energy Ke is equal to half mv squared, where m is the mass of the body and v is the velocity. At equilibrium position, kinetic energy is maximum, that is, Ke is equal to half mv subscript m squared. V subscript m represents the maximum velocity. But recall that the total energy of a simple harmonic motion can be calculated by Pe plus Ke or Pe maximum or Ke maximum. Therefore, for a mass attached to an elastic spring, the total energy is equal to the potential energy, which is half Ks squared, plus the kinetic energy, which is half mv squared. Also, it is equal to half Ks squared, which is the maximum potential energy, and also equal to the maximum kinetic energy, which is given by half mv subscript m squared. Now, equating these two expressions, we have half Ks squared plus half mv squared is equal to half Ka squared. To make velocity v the subject of the formula, we'll first of all subtract half Ks squared from both sides. This gives us half mv squared is equal to half Ks squared minus half Ks squared. Factoring out k over 2 from the right-hand side of the equation, we have half mv squared is equal to k over 2 bracket open a squared minus s squared bracket closed. That's to show that k over 2 is common to half Ka squared and half Ks squared. In order to eliminate half m on the left-hand side of this equation, we multiply both sides by 2 over m, and this leaves us with v squared is equal to 2 over m bracket open k over 2 bracket open a squared minus s squared bracket close bracket closed. On the right-hand side of this equation, 2 cancels out 2 to give us v squared is equal to k over m bracket open a squared minus s squared. And when we take the square root of both sides, we'll have v is equal to square root of k over m bracket open a squared minus s squared bracket closed. So the velocity of a mass attached to an elastic spring is v equal to square root of k over m bracket open a squared minus s squared. Recall in the part 2 of this topic, we found an expression for calculating the velocity of a simple harmonic motion to be v equal to omega square root of a squared minus s squared. If we compare these two equations for solving velocity, we will have omega square root of a squared minus s squared is equal to square root of k over m bracket open a squared minus s squared bracket closed. If we square both sides to eliminate the square root, we have omega squared, square root of a squared minus s squared all squared is equal to square root of k over m, bracket open, a squared minus s squared all squared. And we know that this square will cancel the square root, leaving us with omega squared, a squared minus s squared. And the square will also cancel the square root here, leaving us with k over m, bracket open, s squared minus s squared. In order to make omega squared the subject, we divide both sides by a squared minus s squared. This gives us omega squared is equal to k over m, bracket open, a squared minus s squared over a squared minus s squared. And when we solve through, this will cancel this, leaving us with omega squared is equal to k over m. Taking the square root of both sides to make omega the subject, we'll have omega equal to square root of k over m. And of course, if we make k the subject here, we'll have k is equal to m omega squared. So the angular velocity omega for a mass attached to an elastic spring is given as omega equal to square root of k over m. But recall that the period for a simple harmonic motion t is equal to 2 pi over omega. So substituting square root of k over m for omega in this equation, we have t is equal to 2 pi over square root of k over m. This is the same thing as 2 pi over square root of k over square root of m. Simplifying this, we have 2 pi over 1 times square root of m over square root of k. This gives us 2 pi square root of m over k. So the period for a mass attached to an elastic spring is given by the formula T equal to 2 pi square root of m over k. Having done this, let's go on to solve some examples. Example 1. A block of mass 4 kg is attached to a spring and undergoes simple harmonic motion with angular velocity of 2.5 radians per second. The amplitude of the motion is 2 meters. Calculate its elastic constant K and the total energy of the motion. Solution. From the question, our mass m is equal to 4 kg and the angular velocity omega is equal to 2.5 radians per second and the amplitude of the motion A is equal to 2 meters. We are asked to calculate the elastic constant K and the total energy of the motion. For us to calculate the elastic constant K, we use the formula omega is equal to square root of K over m. Making K the subject, we have K is equal to m omega squared. Substituting the values given into this equation, we have K is equal to 4 times 2.5 squared. This gives us 25 newtons per meter. Next, we have to calculate the total energy of the system. And since the amplitude of the motion is given, we'll be using the maximum potential energy to calculate the total energy, which is E is equal to half Ka squared. Substituting the values into this equation, we have total energy E is equal to half times 25 for elastic constants and 2 squared for A squared, that's amplitude squared. This further gives us half times 25 times 4. 2 squared is equal to 4. Solving through, we have 25 times 4, which is 100 divided by 2, which eventually gives us 50 joules. Remember, energy is measured in joules. Example 2. The potential energy of a pendulum bulb undergoing simple harmonic motion is 25 joules at maximum height, h equal to 0.6 meters. If the acceleration due to gravity is 10 meters, calculate A, the mass of the body, B, the maximum velocity of the bulb, and C, the maximum kinetic energy of the bulb. Solution. From the question, the maximum height is 0.6 meter, and the acceleration due to gravity G is equal to 10 meters per second. Now note that the potential energy at maximum height is given by the formula mgh is equal to 25 joules from our question. Now the first thing we have to solve is the mass of the bulb. And to solve this, we'll use this equation, mgh is equal to 25 joules. And when we make m the subject of the relation here, we have m is equal to 25 over gh subscript m. Now substituting 10 for acceleration due to gravity and 0.6 for hm, we have m is equal to 25 over 10 times 0.6. This gives us 4.2 kilograms. The next thing we have to solve is the maximum velocity of the motion v subscript m. Since this motion involves a simple pendulum, the maximum velocity v subscript m is equal to square root of 2gh subscript m. When we substitute the value of g for acceleration due to gravity and maximum height h subscript m into this equation, we have v subscript m is equal to square root of 2 times 10 times 0.6. This is equal to square root of 12. And square root of 12 is equal to 3.46 meters per second. So the maximum velocity for this motion is 3.46 meters per second. Next, we have to solve for the maximum kinetic energy, Ke. And the maximum kinetic energy is given by the formula half m v subscript m squared. And going on to substitute the values for these parameters, we have Ke maximum is equal to half times 4.2 for the mass and 3.46 squared for v subscript m squared. This gives us 25.14 joules, which is approximately 25 joules. Having solved those examples, let's go on to see some concepts related to simple harmonic motion. The first concept we have to look at is damped motion. A body undergoing simple harmonic motion moves with a natural frequency denoted by f subscript o. When this natural frequency is forced to reduce by an external force, we say that the motion is a damped motion. The next is forced vibration. A vibration induced on a body undergoing simple harmonic motion by an external force is called forced vibration. And the frequency of a forced vibration, called forcing frequency, is denoted by f. Finally, we have resonance. Resonance simply describes the increase in amplitude of a body undergoing simple harmonic motion as a result of the forcing frequency f coinciding with the natural frequency f subscript o. Having said that, we've come to the end of this class, but before I go, let's take a quick summary of what we've done so far. We learned that potential energy is the energy possessed by a body at rest. We also learned that kinetic energy is the energy of a body in motion. Going on, we learned that in a simple harmonic motion, period t is equal to 2 pi over omega, and frequency f is equal to omega over 2 pi. Also, we learned that the total energy of a simple harmonic motion is conservative. Going on, we learned that for a simple pendulum, total energy E is equal to mgh plus half mv squared, or half mv subscript m squared, or mgh subscript m. And lastly, we learned that for an elastic spring with load, the period t is equal to 2 pi square root of m over k. And the total energy E is equal to half ka squared, or half ks squared plus half mv squared. It's test time, and our first question is, the increase in amplitude of a vibrating system when the frequency of an external force coincides with the frequency of the system is called A. Forced vibration, B. Amplitude elevation, C. Resonance, D. Damped vibration. The correct answer is option C, resonance. Question 2. A body of mass 0.02 kg is suspended from the end of a spiral spring whose force constant is 0.6 Newton per meter. If the amplitude of the body when set in motion is 0.3 meter, calculate its total energy. A. 0.027 joule, B. 0.008 joule, C. 0.054 joule, D. 2.5 joules. The correct answer is option A, 0.027 joule. Thank you for your time. This is where I leave you for today. Till we meet again. Bye-bye.